Hello everyone and welcome back. Previously, we looked into how blockchains are immutable. Ever since we have known about blockchains, we know the greatest advantage that they're immutable, they're highly trustworthy, and our information is safe on the blockchains. But why is there a certain need that we want to delete some data from the blockchain? And even if we want to, is it possible to change or to erase some data from the immutable blockchain? So, previously we had a video where we talked about a paper that was about erasure of data from blockchain nodes, where we were discussing that why do we need in the first place to remove or erase some data from the blockchain. There can be two possible answers to this. The first one may be that the governments or the big organizations might think that there is some kind of data, or truly there are many kind of data on blockchain that might be hazardous to us or to the society and to the organizations or to the governments. It might be some cause that the governments or the organizations don't want that data on the blockchain and they want willingly to delete or erase that data. The second possible reason can be the storage issue. Ever since we are using blockchain, we are using a lot of storage. So we are pushing data onto the blockchains, but what about storage management? So imagine if you're working on the blockchains since 2012, so till 2022, there are a lot many years have gone by and a lot of data has been pushed into the blockchain since then. So what about the storage? Imagine that the data that was stored back in 2012 might not be of any use to us in 2022. And what is it doing there sitting in the blockchain just consuming our storage? Right. So in this paper by many great people like Peter Hillmann, Marcus Knupfer, I'm sorry if I don't take the names correctly, and Erik and Andreas from University Munich, Germany, they've gotten together for this wonderful paper, and it's really simple to understand and mesmerizes me about how people think about the problems that are once thought to be unsolvable, like a blockchain once thought to be immutable, how they have come about different approach to delete the data from the immutable blockchains. So let's go ahead and give it a run through of this paper about what approach do they suggest. So first, the storage issue is a really big issue for unwanted data on a blockchain. And what if it does not get removed naturally? There is an approach that they call selective deletion of single entries in a blockchain. Uh, a brief about that is that the previous data of a chain is summarized and is stored in a new block, leaving out the unwanted information that we want to delete. Then the summarized block is just kept and the previous data that is previous to that summarized block is deleted. The marker from the starting of the deleted block is just pulled and just it goes a shift, I would say, to the starting of a new block. That's how the data gets deleted. And the deleted data that we want to remove is not passed on to the new block that was created or summarized block, as we'll see next. So if you don't get it right now, you'll get it once we go through this whole thing. So Ethereum network has extended the blockchain technology by the Turing completeness in 2015. It allows execution of programs decentralized and to store so-called smart contracts in the blockchain. So usually the Ethereum blockchains and all we talk about are storing smart contracts on the blockchain. That's the form of data we have. The advantages are decisive in terms of security, traceability, and not requiring a third party. Those are the main advantages of blockchains and storing data on blockchain, right? So the most important properties of blockchains are the trustworthiness and reliability based on immutability of data. By concatenating data sets in form of blocks using hash value, it is not possible to manipulate a block within the blockchain. Thus, the order as well as the content of the blocks are fixed. So that's why we call it the immutable blockchain. To ensure the absolute correctness of the blockchain, it has to be completely available starting with the Genesis block. So what's this Genesis block? It is simple that the first block of a blockchain, the origin block of the blockchain is called a Genesis block. Therefore, the blockchain is often called unhackable. However, a change in blockchain is possible but becomes less likely with the increasing number of confirmed blocks. So we can say that the length of the blockchain, the more the length of the blockchain, the less possible it is to change something in a blockchain, because if there are less number of blocks, you just have to change something in one block. It might not be carried forward and forward and forward, but if it's a very long chain and you have to change something in the start, it will hinder each and every block till the end of that blockchain. So the blockchain attribute immutability represents in these cases rather a problem than an advantage. So we have a lot many advantages of a blockchain, but what are the problems with immutability? So researchers say that Bitcoin blockchain contains pornographic content. This is possible because blockchain transactions allow a variety of non-Bitcoin related data to be stored alongside. Since a full node must be downloaded, the entire blockchain, in order to work on the network, the illegal content is also downloaded. So that's where this immutability is actually a problem rather than an advantage. Further, the growing size of blockchain makes the operation very difficult in the long term. Dependent on the storage space and the network bandwidth, the cost of operation or the storage increases multifolds. So the Bitcoin was released in 2009. It has almost reached the blockchain size of a 300 GB. That's a really old statistics if we go through this paper now in 2022. So you can think about how much storage a blockchain might be taking, a Bitcoin blockchain is taking. So in this paper, they have a concept to delete the unwanted data in running a blockchain. The blockchain will forget that this information instead of direct deletion to keep a trusted chain. So it's like it forgot the information but did not directly delete it. Though this approach works independently of the network infrastructure and the consensus algorithm of the blockchain. Next is scenario and requirements. The Journal Data Protection Regulation, called GDPR for short, was adopted in May 2016. The objective was to be like the detectives that standardize the handling of personal data of European citizens with and outside the European borders. Among other things, especially the right to erasure was introduced in Article 17, and it is very important. So any data that is in a blockchain or anywhere, if anyone is storing some kind of data or in the cloud, it has to be some standardized way of handling the personal data of some other people. If you're a company or if you work for some company or you're getting the data from the users. So to illustrate the problem, let's focus on use case of logging and auditing. Logging describes the automated recording of system states, product data, or other process information. This makes it possible to trace the actions by a computer system for humans. So it's simple that if you're working somewhere, you really go in the morning and you just log your attendance there. That's the login, simple. So that system or the machine is recording your attendance and you are the one who's giving the data to them, right? Based on this, we obtain the following requirements. Uh, Authenticity, the act of confirming the truth of data entry. Redundancy of data, storing the information multiple times to be fail safe. So every time I am in and out of my office, I have to swipe that card. Delete on request, a selective erasure of entries or blocks with less effort. Scalability, the system runs for long time independent of the amount of users and the blockchain size. So it has to be scalable. In the following, we decide between deletion and forgetting of data. Difference is that deleting is on purpose, while forgetting is delayed procedure. Nevertheless, if a user of data systems do not follow the rules of erasure, any information published could be stored forever. So it has to be a procedure for deletion as well as for forgetting that data. That is a kind of delayed procedure, right? So what's the related work to that? The most promising techniques are the off-chain transactions, since interactions with the main chain are comparatively expensive and time-consuming, and the whole network has to reach a consensus. During off-chain transactions, digital tokens are exchanged and moved without being recorded on the main chain. So that's kind of thing that people have worked upon. And another possibility is that not private user data are stored in blockchains and only the hashes of the user data for possible verification. So the data is actually not stored, only the hashes are stored there, right? So I'll just skip to this and to the main concept of this paper, that is, in order to fulfill the requirements, we extend the functionality of the blockchain by creating summary blocks at regular intervals. So that this is the best part. So look into the figure 1 on the right hand side of the screen. You'll see two blocks each having some headers, the block number, timestamps, their previous hashes, their current hashes, the data, the Merkle root that they have, and the amount and the data listed, right? But the third block is actually the summary block that have the summary of both these blocks or the previous blocks coming from the summary block, and it's all summarized and stored in the summary block. So what happens is that in the time frame when the size of the blockchain is increasing, what we can do is that every certain time steps we can make these summary blocks so that we can delete the previous blocks and just keep these summary blocks for references. So it will actually save us a lot of storage memory. So let's read ahead is that we extend the functionality of blockchains by creating summary blocks at regular intervals. Afterwards, we present the concept which gives the users of the blockchain the possibility to delete their data on request. This is done after a certain time or with a delay, and therefore we then describe the process to limit the length of the blockchain and to delete on request. So let me take you to the first and foremost background and the consensus algorithm, that a direct deletion of individual entry or a block destroys the hash chain of a blockchain. So if you think that you directly would go into a blockchain and delete certain data, that is not possible because it would lead to inconsistency, corruption, and loss of trustworthiness. If the data from the chain is lost, the chain will get broken and its trustworthiness is gone. Your data is open to all. The information could no longer be completely traced back to the first block anymore because the chain is broken. And here the first block is called Genesis block. I've already told you. To be able to delete individual entries on request, the blockchain have to be able to forget or lose information with intent. Therefore, a novel concept is necessary, whereas the action of deletion is approved by trusted anchor nodes. So trusted anchor nodes are like the guardians of the blockchain. So these are elected groups of trusted nodes. There are certain communities, might be some non-profit organizations, or maybe certain members who have already worked on the blockchain, but they really have like a say in the whole scenario, right? One of the main processes of the distributed system is to agree on common consensus to come to a common conclusion. The presented concept is based on this functionality independent of specific consensus algorithm. The agreement on the same blockchain is usually done by some core nodes that are called the anchor nodes, right? They are the anchors of the blockchain. Among other things, the block number alpha addresses a specific block in the chain. It is used to execute a certain function on fixed blocks by a node. We'll understand that a bit later. Then is extension with summary blocks. So we already know what are summary blocks and so in the first step, the blockchain is extended by a special block type. It's called the summary block. It's given by the summation sign. It consists of deterministic information only and does not include external or additional information. A summary block is periodically created by each node itself. So it's periodically created. So we don't need to call in for summary blocks each and every time. It's periodically created. So for example, every 10th block, right? These blocks are integrated in the blockchain like normal blocks. So figure 1 shows the example. We have already seen that here. As we can see here is that it can be noted that block number alpha sigma of summary block is increased by 1 as normal blocks. The summary block has the same timestamp tau as the block before. This is mandatory so that each node can be calculated as the summary block with its hash values by itself. So what does this mean is that the summary block has the same timestamp as the block before, so that when we remove the block before the summary block, it won't harm the chain. So whenever the next chain to the summary block calls for the timestamp one before it, it can actually take in the summary block rather than the block that is deleted. So it won't call for that. As each anchor node has the same agreed blockchain, the summary block will be identical for each node. So we have to maintain that identical thing here, right? So this information can be used to check synchronization by comparing the hash of its summary block. So of course there has to be some problem with the summary blocks as well, because every pros have every cons. So one difficulty with summary blocks is that the nodes must create themselves and still have exactly the same header. As all nodes work together with the same consensus algorithm, this should be always the case. In case of failure, the hash of the blocks are different. It would result in a fork in the blockchain and it would split the network, right? So limiting the sequences in the blockchain. By inserting a summary block, the blockchain can be seen as separated into sequences. The sequence omega is a series of blocks including the summary block at the end of each sequence. So right, so we can say them they are like a sequence. So from the previous block to sigma n, that is sequence omega n. Then from the new block to the next summary block, there is sequence omega n plus 1, right? The length ln is defined as the number of blocks in a sequence omega n. So in a sequence, there will be ln number of blocks. That is the length of the number of blocks, right? A representation of the sequences is given in figure 2. Here we see that the length L of individual sequences omega n is defined constant depending on the application, but they don't have to be, right? It can vary. Regardless of the configurable parameter, the distance between two summary blocks is described by psi L, the length L of a sequence omega. So we don't need to really go into that much of maths. If you don't understand, you can just skip it. So here is the very important interesting line, that if the blockchain grows larger than a specified length L max, the oldest sequence will be merged into a next summary block, right? So it will be very useful in the coming thing is here. This includes the information of the old summary block to be deleted. The copied information consists of the data part of the block as well as a block number, timestamp and everything. So figure 4 is showing you a data structure of the summary blocks, how the summary blocks actually look like. So we have a block number in the header, the timestamp, previous hash and nonce we don't have. Then we have the data and we have like a summary of entries of each and every block that has merged into this summary block. So the new genesis block will be the block after summary block of the sequence to be deleted. A marker M that is used to indicate a shifting genesis block holding the block number. So the marker would also shift. As this block is part of the blockchain, it is a trusted anchor from the left blockchain part already approved by the anchor nodes. Afterward, the old sequence would be cut off and deleted from the blockchain, and currently the same information is still in the blockchain and the chain is still valid and complete because that whole data still exists in the summary block. So even though we have cut off from the previous blocks, we still have the data in the summary blocks, right? So you can see here is this dotted ones, the marker genesis block M old, this dotted ones have been removed, while this summary from this summary block has been appended here. The summarization, after exceeding the specific chain length, the first sequence will be deleted after the content is copied into a new summary block. So it's deleted after the content is saved, right? So the data part of the summary block has the following structure as figure 4, whereas the content is copied from the original blocks. So the block number, timestamp and the entry number are kept the same as integrally. So these three, the block number, the timestamp and the entry number are kept the same, so that there is still synchronization in the blockchain. Next is deleting information on request. To enable deletion of specific information, a participant needs to be granted some additional functionality to send a delete request. So once we send a delete request, it is accepted by certain anchors which have that authorization to authorize us to delete something or to make a delete request, and then it is made sure that the entry is either located in the summary block or where it has to be deleted, or it's just certain if it can be deleted or not be deleted. So everything is kept into mind before deleting or making a deletion. So this follows the same procedure as normal entries and transactions. The associated data set to be deleted is referenced by the block number and the according entry number in which the data set is stored. It may happen that an entry is located in the summary block. This must be taken into account by also considering the data records in the summary blocks. So the complexity procedure is linear and very low as blocks are references directly by numbers. And regarding the deletion of information, there are two aspects of authorizations and semantic cohesion that need to be considered, right? So let's just give it a try of challenge of delayed deletion and possibility of temporary entries is addressed. So let's see what kind of challenges do we face. The first thing is authorization. So when we want to delete something on request, first thing we need is authorization to delete from the blockchain, right? For authorization of privileges, it can be applied as role-based concept with corresponding user signatures. Particular reference is made to authentication approaches based on the blockchains. For example, the anchor nodes of the quorum work together as a basis of trust and are jointly granted full administrative privileges. These receive a master signature. Based on protocol for consensus-based voting, the quorum dictates the requirements and constraints for addition of the editing. These can be identified by comparing the signature of the user and the stored signature in the data entry. So the system checks if the signatures share the same key and the privileges are given according to the role-based concept. According to the consensus of the anchor nodes, a deletion request is approved and entered in the blockchain, right? So the signatures that are given by the user and that are already stored in the data entry, they have to be the same. So the keys have to match so that you can get some administrative access to make some deletion or to enter the blockchain. Semantic cohesion. Semantic correctness of the blockchain has to be proven by quorum before a deletion takes place. A deletion request can only be granted if further transactions do not rely on it. So as I said, if you want to delete something from block 3 and there are just blocks till number 10, there is high chances that you won't get the privileges to delete the data in the block 3. But if you have like 300 blocks or 3000 blocks and you want to delete some data in 3 that does not rely on the data in the 3, that does not have any effect on the data in 3000 or 300 block, you can easily get the access to delete that data. A deletion request of such chain part of transaction chain can be approved by signatures of all dependent parties, and so these entries become often and in the meaning of the content. So there may be parts that if you want to delete something, there might be chances that it has multiple people or multiple parties dependent on multiple parties. So we have to take an approval from all the dependent parties. Next is delayed deletion. So in this case, deletion means that the information is not deleted immediately. For the moment, the specified data is marked to be deleted, so that when we make some sequence of summary blocks, that marked data for deletion is not considered, right? So marked data set will be deleted when the sequence gets too long or too old. So here is a sequence is considered old enough and the information to be deleted is no longer included in the corresponding summary block. So here is some kind of technique that they use, that if L beta is greater than L max, then L beta new is equals to L beta old minus L mu 1, right? So next is to prevent a log delay in deletion. A possibility is to extend the blockchain with empty blocks. So there is another thing that you can do is, so if you want to prevent long delay in deletion, you can just increase the size of the blockchain and by adding empty blocks. So now the blockchain thinks that the blockchain is too long and that data might be old enough so that you can finally delete that data. This can be done by regularly adding empty blocks after a time interval if no transaction has occurred. To avoid shortening the blockchain too much, a minimum length or a minimum number of summary blocks can be specified for remaining blockchain. Another criteria for ensuring that sufficient data remains in the blockchain is minimum time span coverage, so that there are two possibilities to determine the length of the blockchain, by time and by the summary or block quantity. So the length of the blockchain can tell us, can be known by the time, so that this much time has elapsed, so there might be this much time interval has elapsed, so there will be these many blockchains, or the length of the blockchain would be this, or the summary, there are these many summary blockchains, so we can find the length of the blockchain, right? So new sequence in the blockchain may be created although the oldest sequence is not yet old enough to be deleted. This creates empty summary blocks. This case, for example, occurred at the beginning of the blockchain. However, multiple sequences can also be combined in one summary block. Next is temporary entries. The current design can be extended by temporary entries which will be deleted automatically at specific timestamp tau or block number alpha has been reached. So there might be things like if you have reached certain timestamp, then delete the entries before that. Or if you reach certain block numbers, then you make a new summary block and delete the preceding ones, right? So it is automatically removed from the blockchain and does not need additional authorization. So you don't have to wait for a long time to just make a deletion. For evaluation, they have took a client server based system using Python and Java. And in order to be language independent and to get reusable components, the middleware technology of Corba is used. So what they have done is, if the sequence reaches a defined length, a summary block will be created automatically and includes the check about the blocks to be deleted. So they have example here that say there are three people, say Bravo, Charlie and Alpha. So let me just take their names in the specific order. It is Alpha, Bravo and Charlie, three people scenario, and here's a test setup. So they say that the user Bravo requests deletion of its entry in block number 3 and data entry 1. Right? Since the issuer of the entry to be deleted matches the user in the deletion request, so the corresponding entry is not transferred to the summary block. Hence, the next action is the deletion. The first and the second sequence of the blockchain is merged into the last summary block, and the entry from the block number 3 is not copied because it's marked for deletion. So let's see, I have an image over here. It is right here, right? So you can see in the figure 5, there is a header number 1, header number 2, and there is a summary block. So once we have is that we want to delete a data B from this one, that's in red. I hope you can see it. It's in red, data B. So you can see when this whole thing becomes summary block, a new summary block on selective deletion, this comes into this new summary block, and you can see we cannot find any data B here. It has been removed from here because it was marked for deletion, so it is not included in the newly created summary block. So the colored mark entry is not copied into new summary block due to the delete request. The first sequence will be deleted after the component is copied, right? So what are the achieved enhancements that they got is data reduction, deleting and forgetting unwanted content by not copying the information to new summary block, corrections, so you can make some corrections to the wrongly submitted data, reorganizations, possibly to reorganize information for better scalability, and summarized information. We get a lot of summarized information and we don't need to keep a list of all the data, and we just keep working from the summarized data. And here's also some console outputs. So you can see we have Alpha, Bravo and Charlie in the starting, so like the current status, and once the deletion has been done, you can see the Alpha and Charlie only remains. We can't see any Bravo over here, right? Next is recovery. In case of cryptocurrencies, it offers the possibility to make lost coins usable again. It means not for a single user but for the entire blockchain system to prevent a system shutdown in the long term. Saying that, we can now discuss some strengths and weaknesses. So it's something called hamper 51% attack. What is that is, most known attack on blockchain is 51% attack, where the attackers have the control over 50% resources to create new blocks or manipulate the block order. So you can see over here in the figure 8 console output is that after alpha, you see alpha and you say Charlie, right? So it means that there has been creation of a new block over here. Console output one cycle ahead without deletion request is in the summary block, right? So there is the output is one cycle ahead of it, means there has been some change in the blocks, manipulation in the blocks. Since the old sequence in which the information was stored is deleted, there is no new possibility for new nodes to validate the correctness of the most current summary block. To counter this possibility, we make use of summary blocks to store data more than once, or at least a Merkle root, or as reference for validity to reduce the amount of data. So each entry that is longer than L beta by 2 in blockchain has at least L beta by 2 confirmations at each time. The trustworthiness is given even if the oldest entry is combined in the latest summary block. This hampers 51% attack against a blockchain without summary blocks. As for an attacker, it is not enough to run the attack for only one block. Right? So in short, we can say the longer the blockchain, the more summary blocks there would be, and subsequently it will be more trustworthy. Right? So earlier what we were doing is we were just taking these blocks and we were creating a summary block. Now what they're doing is they're taking these summary blocks as well and they're combining these all, and we are getting here a new summary block. So that's how we are hampering a 51% attack. Next is size of the summary block. So we can say that over the time, it is true that the summary blocks would always also become larger in size. So as the number of blocks increase, the size of the memory blocks will also increase, the summary blocks. The creation of these blocks can take a long time and depending the amount of the data to be copied. To structure this information, what they did is, in addition to copying of much information can be avoided by working with the hash references. So rather than copying the whole data, just copy the hash references to decrease the size of the data to be stored. To summarize the content, as often the result is mandatory to be stored, not every single transaction. Right? Next is extending consensus algorithm. This can be prevented if the nodes only accept a blockchain which is traceable from its current status quo. So if the blockchain is traceable, you just have to make it say that it is a current validated blockchain. So how we can isolate some evil nodes? So there are some kind of attacks called ellipse attack or Sybil attacks. How we can isolate some of those nodes where the tracker tries to separate the participants from the network and control the nodes somehow. So that is also one thing that is actually the way where blockchains can be, they can be surrendered in a way, right? Ascertaining the quorum and reaching consensus. So there can be some problems, especially when there is selection for anchor nodes for a distributed system, because for different scenarios, the case might be different for selecting some anchors as well, right? So that's it for this whole thing. It talks about how deletion from blockchain can take place while maintaining its attributes like trustworthiness and consistency, how we can follow the laws of European Data Protection Act and keep our data safe, and how we can delete some data by using summary blocks and creating summary blocks. And we had a little bit code over there to look about how this paper was created and how we can actually make a prototype of how to delete the data from a blockchain. Other than that, we looked into some pros and cons. About 51% of the attacks that happens where the attackers take control over 50% of the blockchain nodes, right? So we have gotten through all of this and I hope you really love this paper. Do give it a look and Thank you so much for joining in. I hope it was an interesting one for you, and I hope to see you soon later. Till then, keep learning.